to report on is mainly based on a paper, or preprint I should say, that came out very recently with quite a number of collaborators: Daniele Dorigoni, Mehregan Doroudiani, Drewitt, Martijn Hidding, Oliver Schlotterer, who will speak later, Leila Schneps, she's also here, and Bram Verbeek. And the title of the talk is Iterated Integrals in String Theory. So let me draw you for a few slides just a very rough picture where this comes from in a physical context. So one thing is that string theory has this nice feature which is called string perturbation theory, where you draw some nice Riemann surfaces and you want to associate numbers or functions to the Riemann surfaces. And eventually it should be numbers, namely scattering amplitudes, meaning probabilities for certain interactions to occur, but at intermediate stages you get nice modular functions, and this is the connection to the number theory and periods here. So these are very important objects just from the point of view of string theory. They tell you something about gravity, they can say something about the theory itself. This is not something that I'm going to report so much about today, but I will focus on the last point here, which is interesting and intriguing mathematical properties. Just to give you a rough idea how these interesting mathematical objects come about. I mean, on the previous slide I just drew pictures, but there's a way of going from the picture to a formula, which involves certain operations that I'm going to briefly sketch. So there's no... Oh, there's... Okay. Captain Hook. Maybe this way around. So...
we didn't find it.
So...
Because you're mismatching. Pointer's over there. Pointer's over there.
The laser pointer. Oh, you want to the laser pointer. This looks heavy. Let's see if I can carry it. Okay, so we start from a torus here with a few marked points. If you map it to the usual fundamental domain for a torus, so you identify opposite sides, and tau is the parameter of the torus, of the elliptic curve. Z is the marked point. And what string theory tells you to do is you have to compute a certain function on this genus 1 surface that I call sigma here, which is constructed out of so-called vertex operators. They describe what are the specific string states that you want to scatter. So this is information associated with what you do at these marked points. So you compute a certain function on this torus, and then you integrate over the modular space of the puncture torus. And the way that we want to do this is we want to split this integral into an integral over the punctures. So these are just the points Z here. And an integral over the fundamental domain for the torus, the usual keyhole region. And in order for this to be a well-defined object in string theory, this part here, which is called the configuration space integral, has to be modular invariant. And this is the main object that I will talk about. So the bad news is, I mean, it's easy to write down, but this integral is not well known. And it's actually not, I mean, nobody knows how to compute this in full generality. So let me focus in a bit more. I mean, what are the objects that enter this kind of configuration space integral that I had on the previous slide? It typically has several ingredients. So one thing is, of course, I'll take the other pointer if I may, excuse me. Can get it to work.
On the left.
Yep. It's not very big, but anyway, so it has different ingredients. So one thing is this thing that I call the Kober-Nielsen factor, which is Kn, which involves a function g that I will show you in a second. So I have parameters Sij that you can think of as just complex numbers. And in general, there will be additional things happening here. For the simplest example that I'm doing here, which is called the 4-graviton example, there's just the number 1 here. But in general, there will be more complicated things. So this function g that appears here is a well-known function. It's the so-called green function on the torus, which you can write either in terms of Jacobi theta functions in this way, so it's doubly periodic, or you can also write it, which is slightly more physical for physicists, as a lattice sum. So this is just the sum over the non-vanishing momenta on the torus. So p is m tau plus n. M and n are integers. 1 over p modulo squared, together with a certain phase factor that I've written out here. this is a function that is doubly periodic. And these Mandelstam variables, Sij, as I say, you can think of them as complex numbers. They're related to the momenta and energies of the physical process. But now the task is to do this integral up here. So you integrate over the punctures, that I, this complicated function of the punctures, and you want to keep tau as a parameter free. And since nobody knows how to do this integral with a full-fledged exponential here, with this full-fledged Covey-Nielsen factor, what you do is you do what is called a low-energy expansion, which means just expanding out the exponential. For physicists, this is the low-energy expansion because these are related to energies, but you can just think about expanding the exponential, and at any order in this expansion, you generate now integrands which are easier to treat, and they give rise to interesting functions. This expansion you can represent graphically, which I will show you now. So you have two marked points, Zi and Zj, and if I draw a line between the two to represent the Green's function or the propagator, I can associate a certain part of the integrand with them by drawing different lines. I will give you more examples in a second. But since this expansion can be represented graphically, and you obtain something that is modular invariant, at the end of the day you will get something that is called a modular graph function or form in more generality. And these are now, this is sort of a, you should think of this as sort of a generating device for giving you nice, interesting modular objects.
That's the same green?
So, very good. So this green here, actually this green here is not the same green.
That one is red.
Exactly, that one is actually red.
The other one is blue.
Oh, this is a blue.
No, the next one is
The
blue.
next slide is blue, okay.
No, also red.
Okay, yeah. So this green here, this is Michael Green, he's still alive, and the other green from the green function, of course. Good. So coming back here, so there's something graphical you can do. You just draw vertices for the punctures, you draw lines with labels, giving you powers of the momenta and the complex conjugate of the momentum, and the denominator with the space factor, and you just string all these kinds of sums together to produce something that will be modular invariant at the end of the day. So if you do that, you generate something. You start now with a graph, gamma, with these labelings. You do this. There is a certain momentum conservation rule you have to apply, and then you get a function C gamma of tau, where tau is not the modulus, still the modulus of the torus. Gamma is the graph, and this function here has nice modular properties. So under SL2Z, it just transforms in this way, where alpha, beta, gamma is of course in the matrix here. And E are the edges, so I just take the labels, A and B labels from the previous slide from the edges, and this fixes this modular weight. So there's a holomorphic and an anti-holomorphic weight to that transformation. Okay. So simple examples are, you draw a circular graph, you put the labels 1, 1 on all the edges, so 1, 1 corresponds to the Green function. And this translates into the following very simple sum, where you apply momentum conservation, that the momentum on one edge is the same as on the previous edge in this case here. You just have one group sum over one overall group momentum, 1 over p to the 2k, if these are k links. And this is, of course, nothing but the non-holomorphic Eisenstein series.
Except the powers. I don't think it's right.
No, it's right.
That's correct.
Yeah, so I put the tau here that you normally would like to see here probably. So this is the convention I'm using here. And similarly here, if you can put also instead of 1, 1, you can put the labels 1, 0 on all of these edges. Then you just get the sum over the holomorphic part of the momentum, and this gives you the holomorphic Eisenstein series, for which I've written out in my conventions here the Fourier expansion. So it starts, it's not normalized with a Bernoulli, or I mean, here there's a prefix in front of the divisors. And this is mainly to fix my normalizations for these functions, actually, this slide, because they will keep coming back. But I mean, this shows you that sort of this whole class of functions, these modular graph forms, they contain many of the examples that you know, but they also contain examples that are not so familiar. And they come up in string theory. So there's just drawing graphs and trying to evaluate these lattice sums leads to some unexpected relations. So it's sometimes not so clear just from drawing a graph whether this is a new function or something related to a function that you have encountered before. And famously, Daniele has shown that if you take this particular thing, which a physicist would call a two-loop graph, is equal to a one-loop graph.
Which Zaghi is that?
Zaghi, what did I say?
There were two greens, so we thought.
Yeah, exactly.
The red Zaghi.
And yeah, so this is something when you just write down the lattice sum representations of these things that is completely non-obvious, and this tells you that just drawing all the graphs that you would generate from string theory is sort of overcounting a lot. So you want to simplify or understand the space of functions that is actually the elementary part of things. And this has been a long, maybe for about 10 years now, a long enterprise involving many people. This list is not quite complete, but it's very long. So just to understand the space of these functions and what are the possible relations. And my talk is also in that direction today. And the approach that I will follow and that I will later use to make contact to iterated integrals is using generating series. So how does this work? This is work with Oliver and Jan Gerken a few years ago. What we do is we introduce specific integration kernels that are singled out, and these are coming from this Kronecker-Eisenstein series that was, for example, studied by Bram and by Levin, where you take, actually I didn't write down the definition, so this Kronecker-Eisenstein series is also a ratio of theta functions. And if you do an expansion in this now extra parameter eta here, or a series expansion, there's one singular term, and then it has it's a Taylor series. And these functions fa, they're doubly periodic functions on the torus. So this is something that is a nice object. It has nice properties. It has nice differential equations like a heap equation and so on. So this is something that you can deal with very well. And this is something that, because this fa here is nothing but the sum over 1 over p to some power, at least for large enough a when this converges, then this is exactly the kind of thing that goes into the modular graph form. So you can use these things here together with the green function in some sense to generate all possible modular graph forms that you want. And this is what we put into this generating series. And this formula here, that looks very intimidating. I don't intend you to digest all the points of it. So what I want to tell you is this is the generating function. So this is an integral over the punctures. The ingredients are this Koba-Nielsen factor, which involves these green functions. And it involves this Kronecker-Eisenstein series string together in a very specific way in the non-holomorphic and the complex conjugate. And the labels sigma and rho here that I have, these are permutations of the group S in n-1 elements. Because you can here sort of reorder the points on the torus. There's no specific ordering of the torus up to shifting one point around. These are relabelings of the points, and you have to allow for all of them. So this is also something that goes into the definition of this generating series. So this is a function that depends on tau. It depends on this extra parameter eta for each of these Kronecker-Eisenstein series. So there are n-1 of them as well, and it depends on these permutations. So this is a gigantic, slightly complicated object, but it contains all the modular graph forms.
What is Zij?
Say again?
Zij?
Oh, I didn't write the definition. Yes, so Zij is the difference between Zi and Zj. Okay.
It was on a previous slide.
Oh, I did write it.
Very fast.
Okay, so, but if you now take this gigantic, slightly intimidating object and expand it out to a certain order in these parameters eta and also these parameters s that appear in the Koba-Nielsen factor, you can generate any modular graph form for any graph that you like by taking suitable parts of that expansion. So this is really a nice compact object. It contains all possible integrands that you can see in string theory. So now we have one object, but the question is how do we deal with that? And here I made one more comment, which when you look at it, you will probably notice that I'm not treating the holomorphic and the anti-holomorphic part completely symmetrically, because here there's some extra tau minus tau bar that I put in, and this is just to fine-tune some modular properties. So this is just a convenient definition. There's no, you're not forced to do that, it's just convenient. Good. So building up to the actual point of the talk, let's talk about the differential equation that this generating series satisfies. So this is the generating series, which depends on tau. If I take the derivative with respect to tau here, I generate something proportional to the generating series itself. There's something acting on it, which I will explain, and there's something multiplying it, which is a holomorphic Eisenstein series. So this is something that will become important in a moment. Let me talk a bit more about what acts on these on the generating series. These elements here, epsilon k, where k is either 0 or 4 or 6 or 8. So this k starts at 4, the summation here. So these elements here, these are the so-called Tsunogai derivations of the derivation algebra that probably many of you have encountered. And these operators here that form an abstract algebra, in this particular case, are represented as matrix differential operators acting on this generating series. So the generating series has this dependence on eta, and these are operators now which see this eta dependence. And this is actually, I mean, we worked this out to some order, that this forms a matrix representation of the derivation algebra. Our formula is actually conjectural, but we worked it out to a reasonably high order to convince ourselves that this was true. It's probably nice to try to prove this, but this is certainly something that one could study more. But now there's this gigantic element eta, sorry, y here, on which you act with this when you do the tau derivative. And you get something which is proportional to this action and proportional to the Eisenstein series. Okay. Let me just write down the abstract definition of this derivation algebra. And they were studied in a nice paper, for example, by Pollack, but of course previous work by Ihara and Tsunogai himself and so on. I mean, there's a lot of work on this algebra. These are the defining relations. So you take epsilon k when k is 2, 4, 8, not very consistent with k and 2k, I'm sorry for that. So these k's here should be even numbers. And if you take the epsilon 0 and you act with them k minus 1 times on epsilon k, you get 0. So epsilon 0 is a nilpotent. It acts nilpotently in this thing. But what is important is that these elements here, they're not free, they satisfy additional relations. And these additional relations are stemming from holomorphic cusp forms. So this is what is in this paper, spelled out nicely in this paper by Pollack. So the fact that these are not free elements is actually quite important when you want to analyze the differential equation. And nobody objected, but when I wrote the generating series here, I wrote y hat instead of y, and there's also a slight redefinition that is very convenient that I did here, but again, this is something that is convenient to simplify the problem. Good. The main point now is, so we're still building up to the general theory I want to show you, is that this is proportional to the holomorphic Eisenstein series. So if you imagine solving this differential equation here by integrating up tau, you see that you will generate integrals of Eisenstein series. And this is something that you sort of guess from this differential equation here, and you can actually check that this works out, and it connects very nicely to work by Bram, who has done a lot of work on non-holomorphic modular forms and also multiple modular values that we already heard about yesterday, in relation to iterated integrals of modular forms. So this is sort of the string theory way or perspective of arriving at the fact that you should talk about some of these modular forms or modular graph forms in terms of iterated Eisenstein integrals. So this is the sort of the main point to take away from this part of the talk, that really this string theory modular graph form construction leads you more or less naturally to holomorphic, to iterated integrals of holomorphic modular forms. So now I will give you my definition of these iterated integrals. The first thing that I need to say are what are the integration kernels, and the integration kernels that turned out to be convenient for us are the ones that are written here, so it's the holomorphic Eisenstein series, and then it's multiplied by a certain function of tau and tau bar, and d tau 1, so these are one-form kernels. Tau 1 is the integration variable. So there's one which we call omega plus, which involves the holomorphic Eisenstein series. There's one which we call omega minus, that involves the anti-holomorphic Eisenstein series. And they also depend on two additional labels here, J and K. K is the weight of the modular form, and J is in the range between 0 and K minus 2, an integer, which in some sense relates to period polynomial constructions and so on. Now, so this is a set of integration kernels that you can use to write down iterated integrals, and I sort of iterate from right to left. So I start with J1 here, and I go to JL over here, where L is what I would call the modular depth, or sometimes it's also called the range of the iterated integral. Okay, so this is a set of iterated integrals that beta plus, beta minus. Beta plus is with a holomorphic Eisenstein series, beta minus is with an anti-holomorphic one, that are building blocks for solving the differential equation that I showed on the previous slide.
And you don't have a mixture of that?
So here I've just defined them sort of pure with one or the other to solve the differential equation. Eventually I will have to have mixes of the two, but they multiply together in an interesting way. So I will give you examples of that in a second. And the reason why I need mixings is because these things here, they're easy to define, but they're actually not modular objects. So to restore modularity, you have to combine them in some way. So here's a combination of the two. So I call them equivariant by slight use of notation. So these are things with good modular properties. They are obtained by combining them, and you also have to throw in some multiple zeta values. The simplest example is here what I would call modular depth 1. So you just take beta plus beta minus, correct a bit with an odd zeta number and a certain dependence on y, and probably y was on another slide and I didn't write it, show it for long enough. I can also write it here. So y is just pi times the imaginary part of tau. So this is, you can check that this combination here is actually transforming nicely on a modular transformation. So I didn't write down the T transformation, which is more or less manifest in this way. The S transformation just shows you that this is something with an anti-holomorphic rate. It just goes with tau bar to some power. So this is depth 1. It's easy enough to do. And of course, you can also relate this to the non-holomorphic Eisenstein series or derivatives, holomorphic or anti-holomorphic derivatives of that. I mean, applying mass operators to it. Good. At depth 2, modular depth 2, things get a bit more interesting. Here I've written down another example, a bit more specifically now. You see there's the beta plus and the beta minus that you would sort of expect maybe from adding complex conjugates together. But there are also mixed terms where you multiply them together. And there are also lower depth terms, again, involving zeta numbers. Here there's depth 1 iterated integral, or just pure numbers depending on tau and tau bar, and this y combination in this particular way. So when you see this for the first time, it's actually a bit, you might ask yourself, where does this combination come from? So why is this the right combination to build in order to have something that is modular invariant? So this function here, this is what I write there, this is actually fully modular invariant, this combination. And I will try to explain in the following sort of the systematics of how you build these combinations and where they come from. Just to connect back to what I was saying in the beginning about modular graph forms, I mean, this actual object comes up in a different modular graph form here with 3 vertices and some green functions in between. It's sort of the main part of this diagram. is expressed in terms of this iterated integral or combination of iterated integrals. So again, it's a useful technique to put them together in a generating series. So here I write down two generating series, J plus and J minus, where the sum is in terms of these epsilon generators and words involving these letters J and K. So K, remember, is the weight of the Eisenstein series, and J is between 0 and K minus 2. So it's a set of all words in these letters that you sum over, and this epsilon parameter that you use as a coefficient in the generating series is a certain element in this in the universal enveloping algebra of this derivation algebra. So you take just elements of this derivation algebra here and just bring them together. So this is the basis that you use for writing down this generating series. The fact that now, as I said before, these epsilons, they are not free, they satisfy some relations, means that not all the elements in here are linearly independent. This is actually something that creates some problems. This is a generating series, and now these equivariant combinations, and this is a result that goes back to Francis Brown and that we have reformulated in this paper, you can put them together in the following way. So you take the holomorphic ones, you take the anti-holomorphic ones, and you take some set of constants in some sense here in the middle, and another map that I call phi SV. So what this looks a bit intransparent, and I will unpack it a bit more on the following slide. But it's just, so this is just taking the beta pluses and the beta minus in certain combinations, and this thing here is throwing in additional tau dependence and zeta values. So this is the same definition again. And indeed, I mean, the key ingredients in this formula here, as I said, is this series in the middle. This contains conjecturally single-valued multiple zeta values, and this very simple tau dependence. This J minus with a tilde means I just reverse the order of all the epsilon letters. And what is also very important and interesting is this so-called change of alphabet, which also does something to these letters epsilon. You can write this change of alphabet in terms of a conjugation. So if you have any series X with these letters epsilon, you can write this change of alphabet phi SV as a map on this series by a conjugation by a certain other series involving these generators that are called, I'll call them zeta generators for now, but I mean, the full zeta generator is actually a bit more complicated. So these are actually generators Z, which exist for all the odd numbers, and this is meant to say Brown, I think. That normalize the geometric derivation.
It's also red.
Yeah,
No brown.
it's somebody else now. So here, so these things that exist for all the odd numbers, they have the property that if you take a commutator with these derivations, with these arithmetic derivations with the geometric derivations, you get something that is completely expressible in terms of epsilon generators. So they normalize these geometric Zuniga derivation algebra. So these extra elements, of course, 3, 5, 7, these are meant to indicate that there are the odd zeta values. They go with the odd zeta values, zeta 3, zeta 5, zeta 7 that you saw on the previous slide morally. So more exactly, so now how do these generators or these Z derivations, how do they enter in this change of alpha? So you just write a different generating series now for these Z generators, you string them together. You multiply them with a certain number that I will decode. And this thing, because the Z's normalize the epsilons, this thing here, if you work it out, it will give you something that is again purely epsilon valued. So now this thing, the number that you multiply it with, uses a few ingredients. So one thing is it uses the so-called F alphabet, which is a different way, or conjecturally different way of writing multiple zeta values. So Francis Bram proved this in the motivic version of multiple zeta values, and not for the real multiple zeta values. So this is a different way of writing multiple zeta values in terms of non-commutative letters, Fi. Again, I is an odd number, starting at 3. And you just write all possible words in these letters, in these non-commutative letters. You apply something called the single-valued map. This is why this SV subscript is here. And then you take this isomorphism, because it's a conjectural isomorphism between multiple zeta values and these F letters. You take this isomorphism to turn this F alphabet expression back into a multiple zeta value. So one thing that happens is that this isomorphism is not unique. And it's not unique, it was also shown in the same paper by Francis Brown, that this non-uniqueness can be parameterized by having as many rational parameters as there are independent, irreducible multiple zeta values. And in some upcoming work that we'll be discussing with the same set of authors, we find a preferred, or you might even say canonical choice for these rational parameters. So this will uniquely fix this isomorphism between multiple zeta values and the F alphabet. The only thing on this slide that I haven't explained yet, and which is written here at the bottom, is what is this single-valued map. And actually, the single-valued map is one of the reasons why it's convenient to go to the F alphabet, because single-valuedness for multiple zeta values is hard to establish using multiple polylogarithms and so on. At the level of the F alphabet, the single-value projection is very simple. You just take a certain word in the F's and you split it in all possible ways in 2, reverse the left factor, and then shuffle them together. As shown, for example, by Oliver Schneps. So this is a very simple operation in this F alphabet. And now you can do this to any word in the F alphabet, use this map to bring it back to an actual number, namely a multiple zeta value. So this is now a very specific expression for this change of alphabet if you put it back into this thing. So this whole slide was to tell you that in this generating series of very complicated iterated integrals with good modular properties, we have a very explicit prescription for these, for how the zetas or the Z generators enter into the combinations that you have to do for iterated integrals. Yes.
So SV is acting on the algebra of the F's.
Right.
And is it a projection? It's not the single value projection, is it?
So it is.
Well, but the projection should be, I mean, there are a lot of terms. It doesn't look. So, I mean, the projection would fix a lot of things, like all of the single value things.
Right. I will
So
show you.
SV squared is SV, or is it not?
Oh, sorry. When I say projection, I don't mean projection in the sense of p squared equal to p. Sorry. I didn't.
Okay, so
Sorry,
it's not.
yeah, sorry. Then I was.
Yeah, that's correct.
Yeah, sorry. No, it's a single valued map. It's not a single valued project. Sorry. Yes. So indeed. So here, this is this isomorphism is sort of anchored on the primitive element. So it's just the single zetas, and applying the map, not the projection from the previous slide. I mean, this single valued thing just produces 2 times f on a single letter. Applying the projection map, sorry, the map here, and then the inverse isomorphism brings you to just 2 times the zeta number. To be fully precise, all of these should be motivic zeta values, but I'm dropping the motivic superscript everywhere here. So this is what it does on the single letter. So if you have double letter words, the single valued map, first of all, produces twice the shuffle product of the 2 things, and then using the isomorphism property here, this just goes into twice the product of single zeta values. Things get more interesting when you go to words of involving 3 letters. So here I've taken an example, 335. Applying this map, which I'm not writing out now, and the isomorphism, you get this specific combination of single-valued multiple zeta values, 335. rational coefficient, and a very specific admixture of the primitive zeta 11 of the same weight. And you might not like that number, but this is sort of the number that comes out of our current work where we sort of make a choice for this isomorphism rho. So that's some preferred choice that fixes this.
How could anyone not like
Exactly. Well, I mean, I can characterize this number as a consequence of something that is nice. So, but then if you work it out, I mean, you get very, very ugly numbers. Good. So one more thing that I would like to say, so it's one more layer of maybe complication, but it's actually convenient to take this Z generator that I've written here and enhance it by adding to it a certain series in the epsilon algebra, which is called the geometric part. The Z is the arithmetic part, so if you combine these two together in a specific way, you get a generator that I call sigma I. You should still think of this as being associated to the single zetas. And this is now a more proper object actually to be called a zeta generator. It combines these, as I say, arithmetic and geometric parts, the Z and the epsilon generators or derivations. And this sigma you can fix or characterize abstractly, again, by some algebraic properties. This characterization, again, includes an ambiguity, but the same ambiguity will be fixed by this similar choice to what we're doing here. So in this upcoming work that we have at the moment, we will also present a unique choice for these zeta generators, sigma I. So, what do we do with all this information? Let's go back to where we started. So we started with this generating series of good modular combinations, which are called equivariant, of iterated integrals, which was a series in these epsilons, which had these different ingredients. So now I've explained to you what this phi SV does. I will have to say a bit more about the thing in the middle. And this is really something that we want to understand, because this is what relates to the building block of the modular graph forms.
But is it the only relation between the epsilons? Or
No, EG. I mean, there's an infinity of relations between epsilons.
But for this fixed weight, there's a...
For this fixed weight, it's the only one.
just the one?
Yeah. Because this is, I mean, if you want to, this is related to the even period polynomial of delta flow. And then if you go higher in weight, you have more cusp forms, the even polynomial, you get more relations. So, but yeah, so this relation means that, as I was saying before, when you expand this out into its components that are called beta equivariant, they don't all appear independently. This is something that might be a bit bothersome. In the paper that came out earlier this month, we have a way of sort of removing the relations, which we call Pollack relations, by replacing these epsilons by so-called generators E, which are free. So we just remove the relation, we make them free generators. We also extend these zeta generators to extended things. If you do this, then the series up here does not only contain zeta values, but it also contains, well, first of all, iterated integrals of cusp forms, and together with the iterated integrals of cusp forms, L values and other interesting new periods. In the physics application, they're all projected out because you always have the epsilon relation satisfied, but from a sort of structural point of view, it's also interesting to consider this generalization. And probably I will have an example a bit later.
But can you remove them afterwards, after integrating? Can you find, so if you ignore the relations, can you kind of compute all this and remove the L values that come from the cusp?
Right, so yeah, I think I will write an example in a moment, but what we can do is we can sort of replace all the epsilons here by E, so where you don't have the relation, you can work out all the objects, where you have L values, that you see whenever the L values appear, they are multiplied by this combination. So once you impose this combination to be 0 again, then the L values disappear. I mean, not only by this, but all the corresponding relations, of course. Does this answer the question?
You will show the example.
Okay. Okay, so, but I will not dwell too much on this, so this is mainly in the paper, because the impression there's already a lot of information. Instead, I will want to spend more time on what is this thing in the middle. So this is an interesting series, which also contains interesting numbers. To describe what they are, and also to connect back to what I was saying about the zeta generators, it's useful to do what we call a change of frame. So the change of frame just uses the fact that there is an SL2 algebra generated by this epsilon zero derivation. There's another one that is called epsilon zero check. I mean, all of this is standard in the literature. And a diagonal element, which is just a commutator of epsilon zero and epsilon check. These three together form an SL2 algebra, standard triple. And you can use them to act on any of these other derivations. And the other derivations form just a k-1 dimensional representation for single letters. And here I've written out the spectrum of SL2 weights just to show that this is a standard representation. So, okay, so we have this SL2. And the reason why I introduced it is because I want to define a group element in SL2, which is written as USL2 tau by just taking the algebra elements and potentiating them in the right way, but now depending on tau. So there's a tau bar explicitly here, there's a y here. So this is just a very specific tau-dependent, not holomorphically tau-dependent element in this SL2 that acts on generating series in epsilon k. So for example, you can take this generating series of these that was in the middle of the equivariant integrals and just conjugate it by this group element, and you will obtain a different generating series. What I also did along the way is I just reversed or reflected, if you wish, the letter of epsilons with the rational coefficient. So this is partly due to different conventions in different papers that we have to do this. So this R you can largely ignore. The important point is that there is this SL2 that acts on generating series in epsilon and produces another generating series in epsilon. This one here I will call the modular frame, and this one I will call the holomorphic frame. And the reason why this is the holomorphic frame is that actually here I haven't written a tau. This series now becomes tau independent. And it's actually the generating series of multiple modular values that was discussed by Francis Brown again. So he was very inspirational for us. So this particular thing just takes all the periods of these iterated integrals in the holomorphic frame. That's why this is called holomorphic. Good. So the fact that this is tau independent is good because there's a chance that we can characterize it more algebraically.
But,
Yes, please.
But it should be tau bar independent.
So this thing is tau and tau bar independent.
Independent.
Tau bar depends on tau.
And the reason.
Sometimes.
Yeah, so
For physicists, yeah.
sometimes, yeah.
Them independently.
Yeah.
Deep down.
Well, some mathematicians don't.
No.
The tau bar? No.
No, I mean, a mathematician writes f of tau, maybe non-holomorphic.
Yeah.
Physicist writes f of tau.
Tau and tau bar. Yeah.
As if it were two independent variables. So,
Yeah.
there is a different belief.
Yeah. But I mean, actually, this thing here, I mean, I should have, in this convention, I should have written tau and tau bar then.
Yeah.
But yeah, so another thing that I wanted to say, so this, I call this the holomorphic frame, not because, I mean, partly because this is tau and tau bar independent, but more so because these are the multiple modular values that just come from holomorphic iterated integrals, as I will show next. Okay, so first of all, this is just, so I acted with this change of frame on this set of constants. I can also act on the full generating series in the same way. So I start from this generating series of good modular objects. I get something else, and this is now no longer modular, but this is again in this holomorphic frame. And the reason again why this is holomorphic is because many of the tau minus tau bars that you saw in the definitions over here will have disappeared, and you have simple tau dependence, which means you have simpler differential equations. So it's easier to study differential equations of this object than of this object. So if you study the differential equations of this object here and translate back to J, you get this differential equation for the J generating series. So again, just the tau derivative is some simple action of epsilon 0 times the epsilons acting on the generating series multiplied by a holomorphic Eisenstein series and some decorations here for the weight. So this is fully equivalent to a differential equation you will find in these papers by Francis Brown, but we've written it in sort of slightly different way coming from this change of frame here. Okay, now there's an important point now. So here, again, this is this holomorphic frame generating series, which if you follow through all the definitions, you can write as this change of alphabet, multiplying this thing in the middle. So I've just moved this U conjugation through the whole definition of I to generate from the B the C. And then there's this generating series of holomorphic integrals, I plus, there's also I minus. And as I say, they're holomorphic because their integration counts are just tau times gk to the tau. There's no longer a tau minus tau bar, something like that. This is where the name holomorphic comes from. And this is just a rewriting of this thing by applying this conjugation with this SL2 change of frame. Now the important point, and this is something we have checked to quite some extent, is that the thing that here is sitting in the middle, this product of this generating series in the Z generators and this set of just constants in the epsilon generators, recombines exactly to give the same generating series in terms of these zeta generators that are called sigma I. So this is a purely algebraic identity. There's no tau anywhere in here. And this gives you a strong restriction between these generating series. And in particular, you can just take this combination here, solve it for CSU of epsilon, of course, by putting the m to the other side. So this tells you that all these interesting constants that enter in the iterated integrals to make the modular invariant can be just obtained from these zeta generators and the Z generators by multiplying our generating series. And as I say, we have done quite expensive checks on them up to triple integrated Eisenstein integrals. But in full generality, this is a conjecture. But what this also tells you is that these zeta generators, they are fully sufficient to characterize all possible constants that do appear in modular invariant iterated integrals. So you can just obtain all the possible information of these interesting constants and periods by stringing together these very simple single zeta objects. So I should stress, I mean, I say single zeta objects. This does not mean that the thing on the left-hand side is just a product of single zetas, because we saw before because of this isomorphism, there's a non-trivial interplay with irreducible multiple zetas. Okay, so to give you an idea of what this implies is, we start again with this zeta generated. We propose we do arithmetic and geometric part. If you multiply out this generating series, you just get, the first two orders, you get this object here. So at depth 1, you just get single zetas. At depth 2, you get double zetas. But at depth 3, you get triple zetas and irreducible single valued zetas. But everything in here, this is what I want to stress, can be deduced just from the structure of these generating series. You can also look at this equation in a different way. So if you knew what this series was, you could use this to determine what are these objects up here, which is also an interesting question because it's not abstractly fixed in general. So you could also read this the other way. If you knew invariant combinations, modular invariant combinations, you could use this to fix it. Okay. So I've been talking a lot about this, these generators. Let me give you some explicit expressions. This is decomposing sigma 3 and sigma 5, corresponding to zeta 3 and zeta 5 into the arithmetic part and the geometric part. And the geometric part is in general an infinite series. There's a certain weight grading that you can pose on them, and actually use only, you can show that you can only, that you only have to fix finite part in here and then use the definition, the defining properties of sigma to fix the infinite series. There's probably a dot 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 that went missing here. The question then is for this arithmetic part, how is this defined? So this goes back to work by Heine and Matsumoto. This is something that normalizes this algebra of the epsilon. So if you take commutators of the z's with the epsilons, you go back to the epsilon algebra. As I said, there's an SL2 in the playing around, so you have written here a certain projector onto SL2 combinations of epsilons. And also this is an infinite series in general. But putting all this information together, you can, as I said, reconstruct all these constants, and here I've written out one particular instance that you get from that, namely at depth 3, because I wanted to show you something with an irreducible multi-zeta. If you multiply out the corresponding generating series, assemble all the corresponding f words, do the isomorphism to multiple zeta values, you will find this combination here being predicted just from the single zeta. So this statement that I was making before really ties very strongly together the occurrence of single zetas and multi-zetas for the iterated and modular invariant integrals. So we're still waiting for the example with the class form. It might be coming up soon. I have it up on an extra slide. I will show you in a second. So here, let me just say, because this was sort of the main point that I wanted to get across. Let me just say in the paper we have a number of different results that I also alluded to. One thing is that there's this connection to cusp forms, and I will show you the example in a second. We actually prove modular invariance of our construction sort of abstractly, not just in examples, using some co-cycle identities. We also have a reformulation of all this structure, not in terms of partial tau derivatives, so not in terms of Cauchy-Riemann equations, but in terms of Laplace equations. And we have a general construction of these equivariant iterated integrals at arbitrary modular depth by applying to, we're using the Eichler-Shimura theorem, but this does not tell us that the constants will have to be multiple zeta values. So we can just show abstractly that there has to be a modular completion, but what the constants are is not fixed by that. So these are other things that, if you're interested in, you can talk to me about or read the paper. Where can we go from here? So one thing would be, we stopped at modular depth 3, so we have here triple integrals. Of course, you can try to do quadruple integrals if you're strong, because we expect there to be some new phenomena appearing there. What would be nice would be to extend these zeta generators to something that goes beyond multiple zeta values. So I have only sigma 3, sigma 5, sigma 7, so only just for the primitives of the single zetas, primitive zetas. When you go to this bigger world where you also have cusp forms, you have different types of periods appearing in the multiple modular values, and you also want to have some kind of zeta generators associated with them, and this is something that is sort of mentioned also in passing in a paper by Bram, but this I think would be a very interesting connection to understand more thoroughly. From the point of view of string theory, going back to what I said in the very beginning, I mean, these things are related to modular graph forms. For the string scattering amplitude, you have to do the integral over the moduli space of elliptic curves, so you have to do the tau integration. And the question is whether you can use any of our results here to do the tau integration, maybe using some kind of Rankin-Selberg-Serge method, because these are not rapid decay functions. There's some work by Mehregan Doroudiani that goes in that direction, but I think there's also more to be learned sort of from an abstract point of view. Normally I would say thank you for your attention, but let me immediately show you
Since
the...
you weren't attentive. If you weren't attentive, you can't.
Yeah, exactly. So I wanted to, these are some extra slides, sorry, ignore that. Somewhere here. Yes. So this is,
No customs yet.
no customs yet, but just to show you another example. So this is, well, first of all, these are just these holomorphic iterated integrals now, where the kernel is just tau to the j times gk. This is the multiple modular value. If you use that to work that out, you will get new periods appearing. So here we've called this one var pi 4,2, 4,14 for reasons which are not fully transparent, but this is, we decided was a good labeling scheme. This is a new number that is independent of any of the multiple zeta values as far as we can tell. And this is something that only appears if you don't enforce the relations of the derivation algebra. So here are cusp forms. You can also look at these modular completions of iterated integrals in this labeling scheme here. And to make this one here modular invariant, you have to add cusp forms. So here I'm just writing the cusp form part. This is what this notation means. And it turns out to be given by a certain ratio of L values multiplying an integral of the Ramanujan cusp form. And I mean, we have many more examples like this, but this is the first instance where this one comes up. So lambda is just a completed L function in the standard way. And this is a ratio of two values. One is one is inside the critical strip, and this is a non-critical value, and in general it will always be of this form in our normalization conventions. So these multiple modular values that enter from getting a modular completion here, modular invariant completion. If you don't enforce the relations of the Tsunogai relations, they will bring in these L values or generalizations of L values as well. So I will stop here without making any claims about attention.